is that how quickly it was frozen. So the time scale of freezing determines this, and we know how it changes with the temperature. So it's called, you know, what is it? With the effective temperature, and we know how it evolves. And recently we discovered how this structure depends on temperature explicitly. So now we have closed the loop. I'll tell you details about later.
Takeshi? So when we did simulations on BZT, we found polar nanoregions, but really the simulation we're showing it's titanium-rich region. In zirconium, not very much. But in titanium-rich, this is where polar nanoregion were, according to the simulation. With your new technique, can you see where this polar nanoregion located?
This is a volume average, so I can't tell you. But yeah, maybe we should compare with this with the simulation. So. But it's not terribly inhomogeneous behavior, dynamic behavior, as I said. The bulk mode, but this mode splitting is very clear. I think this mode splitting is happening in nearly whole volume, and whether it is NPR or not is depends on size. Okay, we are looking at essentially atomic dynamics. So maybe they are small NPR, not large ones.
We found them small.
I see.
Are there any more questions to the speaker? Oh.
In the case of water, there are tens of possibly hundreds of simulations with Carpal simulation, and people always compute the snapshot G, and then they try to see which functional gives a better G. Did anybody try compute the Van Hove or anything like that?
They don't work.
They don't work?
No. So far, exactly right. Most of the model can produce snapshot, but not dynamics.
Why?
We tried, no, it's because it's not designed that way. So they didn't have the information.
It's just a few picoseconds, they can do some picoseconds. So
No. It's similar, but factor of 2 different. Okay? So you may say factor of 2 is small in this scale of 15 order of magnitude. But, it's all models. I compared with many models. All of them more or less are wrong by factor of 2. And we are now getting into this. And this is because of hydrogen bonding. Okay? So water is, as you know, is held up by hydrogen bonding, which even DFT doesn't work because it's highly quantum mechanical. You have to have lattice degrees of freedom and electron degrees of freedom at the same time, so you cannot assume Born-Oppenheimer. So and even the regular quantum Monte Carlo doesn't work either. So it's a major challenge for theoreticians.
So I think we should move on to the next speaker, so let's thank the speaker again. The next speaker, forgive me if I don't pronounce your name correctly, is Drafko Kripyak.
Yeah, it's okay.